Okay. Do the Google thing. Okay, guys, let me have your attention, please, for a second. Okay. So the video from the last class is uploaded to the YouTube. There is one more video that I need to upload that's related to file I/O. I'll do that this afternoon. The templates for that Dr. Gay had promised are also uploaded on the class Dropbox. Casey, is that where it is?
Yeah, I took the ones from 740.
Yeah, that's perfect.
Yes.
So are they on the class Dropbox?
Yes.
Okay. So they are there. Today, Dr. Gay will continue with the second part of his lecture. On Wednesday, there is a quiz. The quiz is going to be over this material, and it's going to come from the PowerPoint presentations, which are also on the Dropbox. So please go and look at them. The videos are there. The presentations are there. Wednesday quiz. After the quiz, we'll talk more about the assignment, final project, details. Friday, I will do a mix between probably review some stuff for the exam on Monday, as well as we can go more over the final project. Monday is going to be midterm, and from there you guys are off for Thanksgiving. All right? Yes?
You sent us an email. I'm a little bit confused by it. Are you formally assigning us to redo a previous assignment as a separate assignment?
No. The email that I sent was since you should really think about using string for your final project. So if you have not completed that yet, take advantage of Mr. Eugene, I think, Clyde? I don't know how to spell it. Yeah, so he should be able to help you with completing the assignments. I am not sure at this point. That's something we'll discuss on Wednesday, whether we have time to stuff in another assignment in between all of this, which then we could talk about redoing one of your assignments from the past. So think about it, see if that would be useful. Yes?
On Wednesday, are we going to go over like inheritance and
Yes, so some of the things that I'm going to cover, we're going to start inheritance. Inheritance in C++ is a little bit more complicated than Java, so we're going to limit the scope of inheritance. And I'm going to go over some other, so we're going to start with inheritance. All right, everything good? All right, so, Gregory,
All right. All right, everyone awake? So last time I talked to you guys about requirements, and I figure we continue that today by talking about everything you need to know to get started with testing and some strategies for taking your requirements and then coming up with test cases from those. That then once you have code, you can apply those, right? So let's get started. So testing is the central activity of most of your entire development process, but testing is fundamentally the process you conduct to assess the quality of the system you're building. It's a search for deviations from some expected set of behaviors, usually what's laid down in your requirements. So when we talk about testing, what we talk about are the analysis of sequences of stimuli and observations. We poke the system, we pass input to methods, or we create environmental conditions the system has to react to. And then we poke it and we see what it does, right? So as we do so, we record observations. We record anything we can about the system. Usually, you take a look at the output coming. If you call a method, you get its output, you check where that output was what you were looking for, but you can check all sorts of things, right? You can monitor internal actions taken by the system. You can monitor power consumption. You can monitor all sorts of things. Anything you can use to analyze the system behavior, and we can take those observations and those stimuli, and we can issue judgments on the correctness of the software. given what we asked it to do, did it give us the right answer? Did it do so within an acceptable time frame? And did it follow any other properties that we laid out that this system must follow to be considered correct? Right? So we usually think of testing as something we do to find problems. You know, we want to know if it gives you the wrong answer. We want to know if something's gone horribly wrong, if it throws an exception, if it glitches out. And that's true. And that's the main point, but that's also sort of half the story. Testing really has two purposes when we're developing software, and those influence what the actual tests end up looking like, right? And the first is kind of the standard case of defect detection. We want to discover situations where the software behaves incorrectly, right? If it does anything that doesn't conform to our ideas of what correctness is for the functions of the software. And so this is something where we're going to be really concerned with rooting out undesirable behavior. We're looking for things like system crashes, buffer overruns, memory leaks, unwanted interactions with other systems, right? Anything that's really nasty and really going to cause this system to crash to a screeching halt. And so when you're talking about defect detection, you're usually talking about checking what are called boundary conditions. Checking extreme input, malformed input, anything you expect to go out and break the software, trying too much input, for instance, right? And in that case, your test cases don't tend to reflect how the system is being used by 99% of the users, but more of a malicious use case scenario. The second case is for verification, right? And that's to demonstrate to yourself and to your customers that the software meets the requirements, that it did, everything we promised it would do. And in that case, there should be at least one test case for every single requirement you come up with. There should be tests for all the system features, for combinations of features that are going to be incorporated in your product release. And if that's the case, your tests actually do tend to reflect normal usage, how you expect people to sit down and interact with your software. Now, there's really no true boundary between these two approaches. It really just informs the mindset you're looking for. Are you trying to kind of prove it works in the average case, or trying to tear this thing down and break it, right? But in both cases, you can perform verification. You can show the requirements are being met through malformed input, through extreme input. And you can also find all sorts of horrible issues just through trying out normal usage. But in any case, you tend to have tests for both goals, and they tend to look a little bit different from each other in how you set about creating them. So there are all sorts of things that get tossed into a test case, right? But from the start, what you need to consider are a few things. Fairly obviously, you need input. You need to make the software do something. This typically takes the form of a series of method calls, often to a single class of your software. You also need to have expected output. You need to have some expectation of what the system does when you pass it that input. If we pass in 2, we should get 4 out from this, right? So you can encode your expectations on the result and use those to check the behavior that actually comes from the software. Right, and then you need a few other things. Basically, it's called a testing procedure. And this includes a few things. This includes any preconditions, anything that must happen before you run the test. Often that's something like a state reset. If you're in an object-oriented language, you'll destroy the class, create a new instance of it, set up anything that needs to happen before you can actually run this test. If you need to log into the system, if you need to initialize a database, those are the sorts of things you do before you start running your actual test. Right? Then you have a series of test steps, things you do to gather data from the system, to gather your observations, right? And then you need a bit of code that compares the actual output to your expectations and ultimately issues that pass or fail verdict. Did we get the result we expected? Did something go wrong here, right? And then typically after that, there might be a little bit of teardown as well, anything you might need to do in advance of future test cases, right? Any questions on this so far? Yes? So when you call the software, it returns output, but your test case itself is usually just going to be a pass or fail kind of scenario, possibly with some additional information on why it failed. In a lot of languages, we won't have much time to go into this today, but a lot of languages have what are called unit test frameworks. And these include language structures called assertions, which you can use to state properties of the output. Whether it's the output must equal our expectation, or general properties like the output must be even or the output must be less than 0. And if an assertion fails, then the unit testing framework is going to declare this a failure and then usually give you a little bit of information on what happened. Any other questions so far? Now, test plans are the cornerstone of this testing process. And these can range in length pretty dramatically. There's not a set structure. And they can range in formality from quick brainstorming exercises all the way down to extremely detailed blueprints for your entire testing cycle. But regardless, a test plan is what your team has in place to assure the quality of the system at the end. Right? And these structure the process of testing the software. So coming up with a plan is your first step in testing. And your plan, regardless of the level of detail or level of formality, needs to address a few things. It needs to address what exactly we are testing in terms of code features. This can be at multiple levels of granularity. This can be at the beginning a very high level because you haven't coded the system. If you just have your requirements, you might have a list of features of the software that you're going to test. Eventually, this might be down to individual methods or even just arbitrary blocks of code within the system. You need an idea of when you are going to test it. At what stage of development, at what stage of completion are you going to start testing this particular feature or piece of code? You need an idea of how it will be tested. What kind of scenarios are you running? Usually this includes things like error cases, things you expect could go wrong. You need an idea of where you are testing, what sorts of environments. And this is something that's easy to forget about with most software, but down to the hardware you are running it on can dramatically influence the execution of your system. So you might want to consider different hard drive, CPU, graphic card configurations, different networking conditions if you have an online component, so simulate different levels of network latency, different levels of security. If you're working with embedded systems, different physical sensors and physical actuators. But regardless, you might vary the type of environment you run this code in just to see what happens. You should have some clue of why you are testing it. What purpose does this test serve? You have a question?
Yeah. Is testing, do you test for efficiency of code?
Yep. Sure you can. Absolutely. If you have requirements on the efficiency of your software, then you have to verify those are being met. So speed, for instance, speed or complexity. If you have expectations on those, if you have to. A lot of, especially embedded systems, automobile systems, medical devices, those sorts of things have really, really strict timing requirements. And you have to be extremely strict about how you test those to ensure those are being met. Right? And also you should have an idea of who is responsible for testing each component of the software. Right? You should assign responsibility so that eventually you have some assurance this is going to get done. Right? So, I mean, that's kind of the basics, right? So we talked some last time about your requirements, and so, there are a million ways to come up with test cases, but probably the most helpful to you right now, and really the cornerstone of how most people test software, is to start with the requirements and perform what's called functional testing, where you run the software and you ensure that it works as expected and meets your requirements. Right? So, requirements-based testing is the idea of taking your requirements and deriving tests from those. And this is usually the baseline for designing test cases. Right, so functional test design can and should begin before you have a single line of code. It can begin from the point that you have expectations on the product you're going to build. So from the point you have requirements, you can start coming up with test cases. You can continue coming up with them, and you can refine these throughout every level of software design and to the point where you are coding it. Right, so this is the best way to begin early on coming up with test cases and coming up with your expectations on the software. Right? Coming up with test based on your requirements is really good because, your requirements are typically your central idea of what the system should be doing when you're done. This is also really good for finding issues like cases where you forget to implement something in your code, right? A missing functionality. It's really good for finding, any case where you have incorrect outcomes of the method, even when it's working in normal situation and normal usage scenario. Right. Now, your requirements usually start as just plain text statements, right? Natural language. And ultimately, we have to arrive at concrete test cases we can execute on the software. So to arrive at test cases, there are two problems we need to solve. And we can do this through the idea of partitioning our option space, our input and output space. Right? The first is that, well, you can't just test your individual requirements in isolation, right? If you have a bunch of natural language statements that relates, at best to some high-level feature of the software, but often across multiple features, you can't just, it's not necessarily a function you can call. It's just something the software has to do while operating. So the test cases need to be expressed in terms of actual features of the software. And we need to identify what features of the software we can test in relative isolation, and then in combination with other features, link those back to our requirements, and then assign inputs and formulate expected outputs from there. Which leads us to our second problem, which is that not all inputs are going to have the same effect on the software. Even if they should technically give you the same kind of outcome, some might draw out faults while others won't. Right? Some will lead to different outcomes than others. And so that's the second layer of partitioning. Right? We need to take the outputs of every function and try and divide those into all the possible outcomes, right? And then take the inputs and match those up by, well, what kind of outcomes can they cause for those features? So it's kind of what our roadmap looks like for creating tests from our requirements. The first thing is that, well, your requirements have to be testable, right? You need to write and refine your requirements and keep refining them until you can come up with test cases that show evidence that requirement is being met. Then we need to figure out what independently testable features of the software exist. What are the things that we know we can call at a high level, interact with at a high level, and test those in isolation from everything else in the system. Basically, what kind of buttons can we press and what kind of outcomes can we observe? For each of those features, we need to know the possible outcomes, right? What's the good, happy path? What are the alternative or exception scenarios that can occur? And what kind of input will trigger each of these? Now, usually, from that point, what we get are a series of abstract test specifications. They tell you should apply this kind of input for each input to a method. From there, right, we need to piece those together to form our test cases, and eventually assign concrete values for each of those hypothetical inputs. You go from, well, you need a positive even valued integer to we're assigning the value of 2 and calling the software. From there, you can instantiate these concrete test cases, run them on the system whenever the code is ready, observe the outcomes, and ensure that your requirements are being met. Okay, any questions? Cool. So your requirement specification can be pretty large and it can be pretty complex. These eventually get to the point where they can be hundreds of pages long. And you want these specifications to be testable, right? So it's nice to come up with tests for each of these to help you refine your requirements, but when it comes down to testing the system itself, it's hard to test those in isolation. A requirement is not the same thing as a piece of code. It's generally more like conditions that have to be followed by that code. So we have to express our tests in terms of what we can make the software do, and make sure the requirements hold when we use that software in the end. Now, fortunately, the reason we write requirements is to come up with the functions of the software and define how those work. So usually we can take our requirements and decompose those into a set of functions and use those as the basis for testing. So an independently testable feature is any well-defined function of the software that can be tested in relative isolation, as isolated as possible from everything else in the system. what we can do is we can identify the functional behaviors as perceived by the users of the system, what functionality is externally visible, right? So we're often not talking about at the method level, but at the level of the software as a whole. What are the features we can use as a user? What can be interacted with? So, I mean, for example, if you take a web message board, right, and it can usually bring up a list of members. And when it does so, it might sort them in alphabetical order. We have, requirements based on this. We have requirements saying that when this comes up, it should be in alphabetical order, right? So if you're testing the site, bring up the menu list would be an independently testable feature. There's a button we can click. It brings up, a list of users, and from there we can ensure that requirements are being met. It should list all the members. It should list them in alphabetical order, right? So in turn from there, you can verify those requirements. Registering for that form would be another independently testable feature, right? Brings up a form, you can fill out the form, you can ensure that the profile is written to the database with the values you entered in those fields, right? But something like sort that member list is not necessarily an independently testable feature, because at a high level, that's not something you can tell the software to do without doing something else. You have to tell it to list the members for it to sort them in order, right? So we can identify these to divide and conquer the complexity of our requirements and the produced system. We can list out these functions we can independently test and use those to ultimately verify that the system meets the requirements for each of those features. Make sense? Now, when we finally go to write the actual executable test cases, the ones that are pieces of code that you can run on the system, those tend to be written in terms of small blocks of code, what we usually call units, individual methods or maybe classes in the software. Now, until we have code, it's hard to tell exactly what those units are. So really, when we talk about independently testable units, we're talking more about capabilities of the software. Verbs, what does the software do? What actions can it perform? So the testable features are something that can change over time as you start writing the code. It depends on the level of granularity you can test at and how detailed your design efforts are to that point. So early on, you tend to look at the software as a big black box. You don't know what the code will look like. So you're not talking about, well, we're going to call this method in this class. Instead, you say, well, fine, we should be able to register for a forum. We should be able to post items to that forum. We should be able to bring up existing posts, right? But as you start to design, well, you start to come up with individual subsystems within your software, and you can start talking about testing their features. And then you can find out what classes are within those subsystems and talk about what features and methods they offer. Right, so over time this tends to get refined down, and your idea of what is independently testable tends to change as you design the software and as you start writing the source code for that software. Now, these tests for these features need to be described in terms of the parameters of those features and also the environmental factors that can influence that feature's execution, right? So, say we have that user registration feature on our web form. Well, it's got a list of parameters, right? Well, you're going to have a first name, your last name, maybe a username, an email address, a date of birth, right, when you go to register. And those are things you fill in. Those, you can imagine when you're talking about the source code, those are going to be parameters to a method in that code. Right, so those are things you obviously have to come up with input for, and then expectations on the outputs. But you also need to consider any environmental factors that can then influence the system's execution. If you're registering users, what else is sitting out there that might influence how the system behaves? Well, there's a database, right? Presumably a database of accounts. If a user is already registered with that username or that first name or last name, well, then the registration is probably going to reject the attempt to enter this new account. Well, so that's an input to that feature, the database. You can imagine there's different permutations in that. A database without the account, a database with this account that already exists, a database where the connection is down. You can imagine a bunch of different permutations on that. But you have to consider not just the explicitly named input to a function, but also anything else sitting out there that can go out and influence the outcome of that function. From there, the key to identifying tests and coming up with those is understanding how those parameters are being used by the feature you're testing, right? And of course, type information is helpful. Even if you haven't started coding, you can start coming up with your expectations here. Well, your first name should be a string, right? It doesn't make sense to call that a float. So, your first name is going to be a string. Your year of birth might be an integer, right? We might have account structures in the database, but also the context these are used is really important as well, right? You might know that date of birth is a collection of 3 integers, a month, a day, and a year, right? But those are also never being used for arithmetic computations, right? You're not going to add the date plus the month at any point. So that context of how it's used is really important in coming up with how you're going to go out and test this. Right, so if you think about something you've all interacted with at some point, which is a class registration system. If you were building this kind of software and you had to test it, what would you guys think would be some of the independently testable features of this class registration system? Feel free just to shout some things out. Guys, over there? Add classes? Yeah. Sorry, what's that? Oh, lookup classes, sure, absolutely. Yeah, so lookup classes, add classes, remove classes, view account holds, right? Those are the kind of things you can imagine would be the features you test in such a piece of software, right? Maybe changing the number of credits or modifying your grading scale, right? So different options you could try. And you can take each of those and run them in relative isolation from everything else, right? You can add a class without dropping a class. Now, for each of those, you need to think about, well, what are the parameters of this feature? What are the things that I can pass input to, in essence, right? So for adding a class, what would you see as some of the parameters of that we could vary? Like the class name or ID or something like that, right? Anything else?
Whether or not the class is full.
Yeah, well, that's not necessarily... So that's an interesting one, actually. So that's not necessarily you directly something you'd pass in, but that you can consider that as one of your environmental factors, right? You might have a class database out there, and that class could either be empty or full or have, some number of people in it, right? So that would be that is absolutely something you could consider a parameter, but one of those interesting environmental ones, right? So just on a direct basis, well, the course number to add, or its grading basis, or who you are, who are you logged in as, right? Your account might have holds on it, for instance, or might already be taking too many credit hours, or some class that already conflicts, right? That course database, you could have try and register for a course that doesn't exist, or one that does exist and is full, right? Or one that you don't have the prerequisites for. So there's all sorts of things you could vary there, and they're not necessarily things that you would name and pass in directly if this was a function of the software, but rather those environmental factors. What's in your database? Who are you logged in as? Right? Does this idea make sense to you guys? Cool. Well, this next step from there is to come up with the input to those parameters. If we want to test the software, we should prod the system and see what it does, right? So we need to know what kind of values we can pass in, right? Now, at first you might just try, well, why don't we try everything? Why don't we try every possible input we could pass into this? You could probably already guess that's not something that's generally feasible, right? If you just take a calculator, take an addition function, right? And yeah, fine, let's try passing every combination of 2 integers. that's not really going to work out. You could probably imagine, even, there is a max integer we can pass in a lot of languages, right? But even given that, you are still talking, that number times that number inputs. Even if you were being generous and saying we could run a test per nanosecond, you might be running tests for thousands of years just to try one simple function, and it only gets more complicated from there. So really, in practice, we just can't try everything. And, really, the addition's the bottom of the barrel there in terms of complexity. Most individual features are going to end up with quadrillions of possible input, and your job from there is to come up with those that are likely to reveal faults, right? So exhaustively trying everything isn't going to work out, but fortunately you don't really need to. The fact is that not all inputs are as useful as others. So purely from the verification perspective, purely from the idea that you can take your requirements and show that they're being met, there's only so many outcomes of a function, and you've got a lot of inputs that are going to lead to the same outcomes, right? So some are going to be fundamentally be better than others at revealing those problems, and we need those inputs. Sadly, we don't know ahead of time what's going to cause a fault, especially if you don't have code, right? But as a start, what we know is that two tests with inputs very different from each other are more likely to reveal fault than trying two tests with very similar input, right? I mean, just think about that for a second. If you had a program that could break, a string down into multiple lines of like 60 characters each, and you grab the test with a 40-character string and a 30-character string, and now you're going to go choose the final one, and we're going to toss in a 100-character string. We can't prove that last one is any more likely to reveal a fault, but it's going to be better than choosing another string that's less than 60 characters, right? You're hitting two different outcomes right there. And that's a start. We're covering a wider range in the input space, right? So at the very base level, tests with different input are favorable over multiple tests with very similar input. And so we should take a good long look at that input space. And ultimately, right, faults are going to be pretty sparse in the input space as a whole. But they're going to be dense in the regions of the input space in which they appear, right? If you try, a bunch of input roughly in this area, you're more likely to reveal fault than if you try something over here. In practice, we can almost always divide this input space into partitions, right? Into logical groups of input based on some criteria, maybe based on the outcome they'll trigger. And the thing is if we do a good job of partitioning, if we come up with an input that lands in a space dense with faults, then we're in good shape. So it goes back to the thing I was talking about last time, the last slide. We should, as a general strategy, favor different input over similar input. And that's a really key idea, trying two very different things, and you're more likely to trigger a fault than if you try two very similar things. Even more so if we think about where those inputs come from, and if we spread out our inputs over these partitions of the input space. So by incorporating a bit of human knowledge in how we partition the inputs, we can try a wide variety of test cases and be more likely to land in one of those spaces dense with faults, right? So by partitioning the inputs, we end up with what we call a set of equivalence classes. And these are tests that are essentially interchangeable from each other. If you have an equivalence class of tests, you essentially test the same scenario, right? They give you the same outcome of a function usually, or they might trigger some behavioral pattern or the same usage of a feature, right? And when we have input from those groups, they tend to test the same thing, and we tend to treat them as interchangeable. So if a test reveals a fault, there's a good chance that others in that equivalence class will also trigger the same fault. Or if you don't trigger a fault, there's a good chance that others in that class won't trigger a fault as well. So what you want to do is come up with tests from each of these possible equivalence classes. Perfect partitioning a test is really difficult to do, right? But with a combination of intuition, experience, and some common sense, you can do a pretty good job at this. Right? if we just think about something simple, say we have a substring function, takes in a string, takes in an index, spits out a string from the beginning to that index. Well, I mean, you've all used something like this before. We have two inputs here, right? We've got a string, we've got an index. What are some things, before I talk about ways people partition these, what are just some things you would try if you're going to test this function? Yeah, try an index of 0, right? It should just give you nothing back, right? Anything else? Something, maybe something greater than the length of the string, for instance, right? Anything else? So I mean, this is by no means exhaustive, but you'd vary the index definitely. You'd maybe try something negative, something greater than the length of the string, just something normal, something at 0, right? Try string, vary the string's length based on your index, right? Because you can tie these together. A string with a length shorter than the index, equal to or greater, right? So just approaching this purely from the idea that, well, our substring could result in, we could get different outcomes from this function, especially a lot of different error cases from this function, gives you right off the bat a lot of different scenarios to try out. So along those lines, what you want to consider are things like equivalent output events, equivalent outcomes of a function. You want to look at different ranges on those inputs, right? If you have an integer input, there are different values you can try. Look for membership in some sort of logical grouping, right? Can we group these inputs based on how they're being used or the context the method uses them in? You can look at the data structures involved. Certain data structures, especially collection types, tend to suggest certain equivalence classes. And of course, considering things like weird boundary conditions or any case where you suspect could cause an error, right? So I mean, the first thing to do is start from your outputs, divide the output into different outcomes you can get, and try to come up with input that produces each of those. If you have a graphic routine, right, you're drawing lines on the canvas, well, you have a bunch of different options for those, and you want to try each of those. So, some thing where you're not drawing a line, or where you're drawing a thin short line, or a thick, red line, or all the different options you can try when performing this function. If you're dividing any input into partitions, it's pretty natural just to look at what type of input it is, and how you could split the values of it into discrete ranges and choose from those. And any value from a particular input range should generally have the same effect, right? If you have, you want to typically look at this in context. If you're passing a 5-digit integer between, so that's going to be between 10,000 and 99,999. Well, you want to try certain things. You want to try something from that range because that's what you're expecting in your method. You also want to try something below that. Try a 4-digit integer, and try something above that. Try a 6 or greater digit integer, right? Or depending on the context, if it's expecting a positive number, try a negative number. Try maxint. Try passing in something that's not even an integer. Pass in a float and see what happens, right? Similar ranges can often come from other data types as well, especially if you're considering things like arrays or other data structures, right? Typically, what you want to try are things like single-valued arrays, different sizes. Try a very large array because those typically cause efficiency issues, especially if you have timing bounds that you need to consider. Try an empty array, right? So these are typically cases people don't necessarily consider and where the behavior of your software can go wrong. And then try things, of course, so that the first, middle, and last entry of your array are going to be accessed as well, because these tend to be partition boundaries, tend to be cases where something can go a little bit wrong if you're off by 1, for instance, in how you access array indexes. Now, somewhat situational again, but also don't forget things that are likely to cause problems. If you've included error handling code, make sure that you actually try that code, right? Pass input that's going to trigger it, make sure the error is handled as expected, and that the system continues to function as expected after you cause an error, right? And don't forget to incorporate those as inputs that you try when you're testing. Exception handling tends to be a pretty known problem area because we don't necessarily think of everything that can go wrong. So as you're testing, really think creatively about how you can take this piece of code and just tear it down, how you can destroy it in any way you can, right? And try that. Because often you will hit something that, even if it's code you developed, that you forgot about earlier, right? Some weird corner case that just your code is not prepared to handle. So really think creatively about how to just destroy this code. Make sure any case where you can pass in malformed input that you can do so, right? So, just another one to kind of throw out there. Just another simple case, right? We pass in 2 integers and we get the max of those 2 back. How would you go about partitioning this? What are some of the test cases you'd try here? Yes? Yeah, for just individual ones, you probably want to consider negative values and positive values. 0 you want to consider because you could have weird handling there. If you're relating the 2 together, the obvious cases are, well, A is greater than B, B is greater than A, right? Make sure that works. A is equal to B, make sure that works as expected, right? And then kind of combine these, right? A is greater than B and B is a negative number, right? So some of these are pretty obvious, right? Yeah. So typically you consider these in isolation, A and B, but also how they relate to each other in the context of this method. And this is going to give you a bunch of different test cases to try out. A lot of scenarios where you can ensure that the code works as you planned it to work. Right. So for each of these independently testable features, you want to identify their parameters, identify representative values for each of those parameters, right? So for each of those, we want to chop them up into different groupings. So now we have each of these individual inputs partitioned. Now for tests, we feed in the combination of inputs, right? So not just a value for one, but a value for all inputs to that function. So from there, we want to form the different possible combinations of those partitions for a set of inputs to kind of get your set of abstract test specifications. If you feed in an input this type and this type, well, this is the outcome you should get. So in coming up with these equivalence partitions, you need to think about really what exemplifies that space of inputs, and make sure you hit the types of inputs that can be passed in. So we have an insert into at a particular index in a list. We expect that to be a 5-digit integer, so we got some partitions already for that just based on that context. We have a list, and there are partitions we can try for that. We'll try an empty one, try one with 1 entry, try one somewhere in our expected range, try something outside of our expected range, right? And then we can start plugging these together. For a test, you're calling a function, so you have to provide input to each of its inputs, each of its parameters. So we start combining this, and we have 3 partitions for n, we have 4 for list. So we're going to start forming every possible combination of these together. And from those, we can start creating concrete test cases by assigning values to each of these abstract specifications, each of these partitions, right? So if we have something where we expect an integer less than 10,000 in an empty list, well, here's our test case, right? We'll try one of 5,000 as our input and this empty list. And so on. Does this make sense? Right? Now, at a base level, the number of possible test specifications can still be extremely high, right? It's that Cartesian product of the representative values for all those variables. So that can grow exponentially as the number of variables in equivalence classes grows. So for a simple system with 5 inputs, 6 values for each, you're still going to have over nearly 8,000 abstract test cases, and each of those could be instantiated into dozens of concrete test cases. So that's a pretty insane number of tests for a simple system, and that's not really going to work. But from there, your next step is to typically go through and start eliminating any impossible pairings, and then identify constraints that can remove any unnecessary options. Usually in this case, you identify any input partition that's going to cause an error to occur, right? And in those cases, it doesn't matter what else you pass in. You're just done, right? So you only need one combination with that particular input combination, or if that particular input partition, rather than every possible permutation involving that particular partition, right? You might consider weird corner cases. Ones that, you don't need to try multiple times. They should work as expected, but you're going to try once just to make sure. And you can identify constraints between these where, well, if you're applying this partition to one input, then this other input must also have a particular partition. And from the remainder, you can choose a more practical subset to apply to your system. Right? And then finally, your last step is to take those and start assigning concrete values. Now, each of these specifications, these abstract ones, can typically take on, dozens, if not hundreds, of concrete inputs. So, you typically don't want to try just one case, but try a few different cases, just to make sure you don't accidentally stumble on something weird going on. To make sure, you get agreement each time. If you change the input, you won't get the same concrete output, but you should get the same type of output if they're from the same partition. And you can verify that that is the case. And from there, narrow down if you're getting any issues, if you're getting any incorrect behavior. Right? So, we are out of time here. Right, so are there any questions before we're done for the day? If you think of anything later, feel free to email me or check in with me or check in with your instructor, who can then get in touch with me from there. And otherwise, I think you guys are good to go unless you have any announcements or anything.
No, you're good.
All right, great.
Wednesday quiz.
That's fine. You don't have to clap. You're good. There we
Coming by.
Yeah, definitely.
Yeah, it's good to see you.
Yeah, definitely. We're not going to show up this Wednesday either, but
That's fine.
yeah. Now we keep traveling everywhere.
That's fun. I love to
Yeah,
travel.
it is fun. No, it's good to see you.
Good to see you.
It's really weird that I keep running into you in classes I'm teaching. But
It's great.
it's fun. Yeah.
Thanks again.
Yeah, definitely. See you later.
Waterfalls.
I'm going to my door. Not my door. I'm going to the lab now.
video lecture and I canceled class.
I got that.
I know